In Lesson 3 of the Abstract Algebra series, I explained algebraic structures with two operations. Among them, the field structure is perhaps the most important one. It is encountered in many applications in mathematics and physical sciences. In this video, I will present an application of field theory to one popular board game, that of Solitaire. Often the term peg solitaire is used to differentiate it from the homonymous card game. Any viewer who has played the game enough already knows that the final surviving peg cannot finish at any place. Using abstract algebra, we will work out explicitly the allowed positions for the final peg. But first, let's present some comments about the game and its history such that every viewer has adequate knowledge about it. The game first appeared in France in the late 17th century. Evidence is found in several artworks of the period. On the screen, we see the solitaire appearing in a 1697 engraving of the Princess Soubise by Claude Auguste Barye. In print, the first record of the game is found in the French literary magazine Mercure Galant in 1697. Today, the game is produced either as a board with holes and pegs, or as a board with indentations and pieces of marble. Of course, computer versions are available. The standard version consists of a cross-shaped board with 33 holes. All holes but one are filled with pegs. The empty hole is usually the center hole. Any peg can jump over an adjacent peg horizontally or vertically into an empty hole, removing the peg which was jumped over. A diagonal jump is not allowed in the standard version of the game. The goal is to remove all pegs but one and the surviving peg to end up at a predetermined hole. In the standard version, the center hole is also the target hole. Since one jump removes one peg, and there are 32 pegs at the start, a complete game contains exactly 31 jumps. A series of successive jumps by the same peg is called a move. Obviously, there are at least three important questions for the game. The first question is, which sequences of 31 jumps consist solutions of the game? Among all solutions, there will be one or more solutions which consist of the minimum number of moves. Hence, the second important question is, what is this minimum number of moves? And the third question is, can the final target hole be any hole of the board? The third question is the one I will answer in this video. Before we move to the mathematical part of the video, let me add a comment which should be obvious to my viewer. The solitaire board may be modified both in size and shape. The figure shows some of the variations that have been used. In fact, there is no constraint that prohibits to modify the board to a three-dimensional one. And of course, a different target hole can be selected every time the game is played, as long as the selection is consistent with the constraint to be presented. Notice that in the French-style board, the empty hole is above the center hole, and the target hole is below the center hole. This choice will be appreciated after the completion of our calculation. Now, let's quickly review the algebra concepts which will be important in the presentation. A group is a set G with a binary operation star defined in it, such that the operation is associative. It has a neutral element, and each element has an inverse element relative to the operation. A group is called abelian if the operation is also commutative. The notation G** indicates the set G without its neutral element. A field is a set F with two binary operations dot plus and dot times defined in it such that F endowed with dot plus is an abelian group. F** endowed with dot times is an abelian group. And the two operations are linked by the distributive property. For a field, the notation F** indicates the set F without the neutral element of the additive operation dot plus. Examples of fields are the sets of rational and real numbers endowed with the operations of addition and multiplication. These fields have an infinite number of elements. There are fields with a finite number of elements. In Lesson 3, I discussed the set ZP, which is related to modular arithmetic. The set ZP represents a clock with p hours. Additions and multiplications in ZP happen the exact way we do them with the traditional 12-hour clock. However, a clock whose total number of hours is a composite number is not a field since there are proper zero divisors. That is, non-zero numbers can be multiplied to give the neutral element of the addition, which is the number p. If we require p to be a prime number, then ZP is a finite field. In mathematics, the fields with finite number of elements are called Galois fields. A finite field with n elements is denoted by the symbol GFN. Hence, the field ZP with P being a prime number is a Galois field. I will defer a presentation of Galois fields for another presentation. Here it's enough to say that I will use the Galois field GF4, whose 4 elements will be indicated by 0, 1, P, and Q. I will also indicate the 2 operations by a plus and a dot, although, obviously, they are not the standard addition and multiplication. The following tables give all addition and multiplication operations between any 2 elements in GF4. It is routine and obviously boring exercise to verify that GF4 equipped with these 2 operations is indeed a field. From the tables of GF4, notice that P squared equals Q, P plus 1 equals Q, and Q plus Q equals 0. Taken together, these equalities imply the following identity. Since 1 and P are the opposite elements of themselves, the previous identity can also be written in another form. These identities are crucial for the application of GF4 to Solitaire. Another property which will be important relates to the powers of P. Notice that P cubed equals 1. This implies that in GF4 all powers of P with exponents, which are positive multiples of 3, are equal to 1. The same is true for negative exponents. We are now ready to apply abstract algebra to Solitaire. In particular, we will make a connection between the board and the Galois field GF4. This idea is due to the Dutch mathematician Nicolas de Bruyne. He presented it in a 1972 paper published in the Journal of Recreational Mathematics. We start by attaching coordinates to the holes. That is, we imagine a rectangular grid and the holes located at the grid's integer points. For the remaining video, I will follow a physics terminology. I will imagine the pegs as being physical particles. Then the solitaire is a system of variable mass. That is, a system that ejects particles. At any given time, we can look at the system and record the position of the system's particles. This is called a state S of the system. The set of states is called the configuration space C of the system. Next, we define a function in the configuration space, which assigns an element of GF4 to any state of the system. This function defines a conserved charge. That is, a quantity which keeps the same value as the system evolves. The proof of this claim is very easy. There are only 4 legal moves for the ejection of a particle: a right jump, a left jump, an up jump, or down jump. For a right jump, the particle at position x, y moves to position x plus 2, y, and the particle at position x plus 1, y is ejected out of the system. If S is the initial state and S prime is the new state, the charge Q changes by the following amount. Notice the factor P squared minus P minus 1, which vanishes in GF4. Similarly, we can prove that Q preserves its value for the other 3 jumps too. Hence, the charge Q is conserved during the evolution of the system. We could do even better. We can construct a second conserved charge. The proof that P preserves its value for any jump is a replica of the previous proof. Now, let S naught be the initial state of the system and Q naught, P naught be the corresponding charges. No matter how the system is going to evolve, the charges must remain fixed. If XF, YF is the position of the surviving particle at the end of the evolution, then the charges of the final state must be equal to the charges of the initial state. These equations form a constraint for the allowed target positions. For the standard solitaire board, the initial charges are 1. To check this, notice that in the standard game, the initial state consists of particles arranged in groups of 3 consecutive particles. But for any such group, the charges of the 3 particles add to 0. For the 2 remaining particles at the center, we can easily compute the total charge to be 1. Hence, the net charges for the initial state are equal to 1. So, in the standard game, the constraint for the allowed target position reads: we conclude that the sum and difference of the coordinates for the final position must be multiples of 3. Therefore, the coordinates themselves must be multiples of 3. And hence, for the standard board, Only 5 holes can be chosen as the target holes. Here is a visual representation of the result if you prefer it. Finally, let me add some comments. 1. The result applies to all boards where the pegs are arranged in rows and columns. 2. Although the result was derived for 2-dimensional boards, it applies to boards in 3 dimensions. In this case, we could define 2 conserved charges per plane. However, we do not need so many charges. 3 charges are enough. It is now easy for my viewer to generalize to an arbitrary dimension. 3. The configuration space can be divided in 16 subsets based on the values of the charges Q and P. Mathematically speaking, these subsets are called equivalence classes and are denoted by the values of the charges between square brackets. Each equivalence class contains states that can be obtained through legal jumps from any other state in the same class. However, a state in one equivalence class cannot be obtained by a state that belongs in another equivalence class. 4. Returning to the French version of the board, the initial charges are Q and P. Therefore, the final state must belong to the same equivalence class. Thus, any target hole must satisfy the following constraints. The position 0, -1 satisfies this requirement, but the position 0, 0 does not. And with these comments, I have reached the end of this presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.